Welcome to The Explainer. Today, we're diving into the absolute extremes of materials science. We're going to unpack the incredible journey of a true supermaterial, zirconium carbide. We're tracing its path from a raw, meticulously engineered powder all the way to the absolute leading edge of hypersonic flight and the blazing cores of advanced nuclear reactors. So let's just start off with a massive question. What kind of supermaterial could possibly withstand the most extreme environments humanity can engineer? I mean, we're talking about the searing friction of atmospheric re-entry at Mach 5 and the punishing, sustained inferno inside a nuclear reactor. Most metals would just melt into a puddle under those conditions. Traditional ceramics, they'd completely shatter from the thermal shock. Well, the answer is zirconium carbide, or ZrC. It belongs to this elite class of materials known as ultra-high-temperature ceramics, and it boasts a jaw-dropping melting point of approximately 3825 Kelvin. Just to put that into everyday perspective, that's roughly 3,500 degrees Celsius. But as we're going to see, having a high melting point is really just the starting line. Here's our roadmap for today's explainer: surviving the extreme, the powder foundation, forging the unforgeable, mastering the microstructure, hypersonics and nuclear power, and finally, the high-entropy future. Let's get right into it. Section 1, surviving the extreme and the powder foundation? At a fundamental level, ZrC is what chemists call non-stoichiometric. You'll actually often see it written as ZrCx because the carbon ratio can fluctuate pretty wildly, anywhere from 60 to 98% of its theoretical max. And materials scientists have to play this really delicate game of trade-offs here. You see, a lower carbon content creates atomic vacancies, literally empty parking spaces in the crystal lattice. This makes it a lot easier for atoms to move around and densify when you're manufacturing it. But if you drop that carbon level too low, you end up sacrificing the final hardness and strength of the ceramic. So how do they make it? Here's the foundational recipe to get that perfect powder, a process called carbothermal reduction. Basically, you mix zirconium dioxide with a carbon source, like carbon black, and bake it in a vacuum at a blistering 1800 degrees Celsius. The whole goal here is to release carbon monoxide gas and leave behind pure zirconium carbide. Now, researchers emphasize that this requires ridiculously precise control over the heating rate and the vacuum atmosphere to avoid oxygen impurities, because even a tiny bit of unwanted oxygen is a massive performance killer in the final material. Section 2, forging the unforgeable. For decades, ZrC was actually held back because conventional hot pressing was just way too slow. It caused the individual crystalline grains inside the material to grow too large, which basically left you with a brittle part. But the real game changer is Spark Plasma Sintering, or SPS. By firing a pulsed DC current directly through a pressurized mold, SPS rapidly heats and consolidates that powder in just a fraction of the time. This lightning-fast process locks in a dense, exceptionally fine-grained microstructure that is so much stronger and more resilient. And this brings us to the absolute bleeding edge of modern manufacturing. Scientists are now breaking free from simple molded shapes and moving straight into 3D printing. Using highly advanced techniques like laser powder bed fusion and direct ink writing, engineers can now create complex, near-net shape components that are just utterly impossible to machine traditionally. We're literally talking about printing specialized fuel cell structures and intricately woven cooling channels right into the ceramic itself. Section 3, mastering the microstructure. Now, to survive at Mach 5, we have to look at a fascinating concept called grain boundary segregation engineering. Scientists aren't just mixing powders anymore. They're literally manipulating the physical interfaces between microscopic grains. By adding very specific dopants, they can pin these boundaries, stabilizing the ceramic at a scale of just a few nanometers. Think of it like microscopic superglue that stops the grains from sliding and deforming under immense stress. But perfecting this material is always a balancing act, right? When you look at the research data on additives, introducing secondary phases like silicon or molybdenum disilicide works absolute wonders for refining grain size and boosting strength. But every single addition comes with a tax. You might risk compromising the phase purity of the material, or you could accidentally make it more reactive to its surrounding environment. Which brings us to ZrC's Achilles heel: oxidation. Despite its absolutely incredible heat resistance, when it's exposed to oxygen at temperatures as low as 400 degrees Celsius, it starts to oxidize rapidly. It turns into this porous, flaky scale of zirconium dioxide that just falls away, offering zero protection to the fresh material underneath. For an aerospace vehicle flying through Earth's atmosphere, this is a literal showstopper. But the solution material scientists have engineered is incredibly elegant. Instead of using pure ZrC, they create a ternary composite coating, mixing it with silicon carbide and zirconium diboride. So when this composite gets attacked by oxygen at high speeds, it doesn't flake apart. Instead, it reacts to form a dense, two-layered oxide scale. And the absolute genius of this is the outer layer of silicon dioxide glass. At extreme temperatures, this glass actually flows like a thick syrup, actively seeping into and sealing microcracks the moment they form. It's a heat shield that literally heals its own wounds in real time. Section 4. Hypersonics and nuclear power. When you get all this right, the resulting property profile of these optimized ZrC components is just staggering. We're looking at extreme Vickers hardness, up to 25 gigapascals, and flexural strength that can top 800 megapascals. But the real standout property here is thermal conductivity. Unlike almost all other ceramics, which normally become better insulators as they get hotter, ZrC has this bizarre, almost metal-like thermal conductivity that actually increases as the temperature rises. This is all thanks to how its electrons behave at high energy states. All of these properties combine to create the ultimate shield for aerospace. Because it can rapidly conduct heat away from the hottest points while keeping its immense strength, it is literally perfectly suited for hypersonic wing leading edges, nose cones, and control surfaces. These components have to survive the incredible aerodynamic heating and shear stresses of vehicles tearing through the sky at over Mach 5, all while shrugging off ablative forces that would completely shred normal metals. But it isn't just about going fast, it's about containing phenomenal energy. Over in the nuclear sector, ZrC is becoming a completely critical safety barrier. Inside advanced gas-cooled reactors, you have these microscopic spheres of nuclear fuel known as TRISO particles, and they need an unbreakable protective shell. By suspending these particles in a fluidized bed and introducing specific vaporized chemicals, scientists can deposit a flawless layer of ZrC directly onto the fuel. This creates a barrier that simply will not degrade in the extreme, hydrogen-rich heat of advanced nuclear propulsion systems. Section 5. The high-entropy future. Looking ahead, we are officially entering the era of high-entropy ceramics. Material science is completely moving away from simple two-element compounds and intentionally embracing chaos. High-entropy ceramics are these massive, multi-element materials combining 5 or more principal metallic elements into a single, highly complex crystal structure. The secret sauce here is what researchers call the cocktail effect. By mixing zirconium with niobium, tantalum, titanium, and tungsten, the resulting alloy doesn't just average out their properties, it synergizes them. When consolidated using that Spark Plasma Sintering technique we talked about earlier, this specific 5-element cocktail actually achieved twice the peak flexural strength of standard monolithic ZrC. It's just a massive leap in structural integrity. And the innovation definitely isn't stopping there. Scientists are actively designing functionally graded materials that transition seamlessly from a metal base to a ceramic surface to perfectly manage thermal shock. They're even using machine learning to predict how these complex microscopic crack formations behave under stress, simulating thousands of variations to find the perfect composite architecture before they ever even step foot into the lab. So which leaves us with a pretty thrilling thought to close on. As we continue to master this high-entropy future, perfectly tuning the exact atomic cocktail of these elements, we really have to ask, what totally new frontiers of deep space exploration, hypersonic travel, and clean nuclear energy will these engineered supermaterials take us to next? The possibilities are quite literally as limitless as the science itself. Thanks so much for joining me on this explainer, and I'll see you in the next one.